Hello friends, I welcome you in lecture number 25 on Laplace transform. In this lecture also we will be using partial fractions to find out inverse Laplace transform. So we consider inverse Laplace transform of this function, which is a rational function division of two polynomials. In the numerator we have 4s plus 5, its degree is 1, and here we have second degree of s minus 1, and this is linear factor, so degree of denominator is 2 plus 1, that is 3. So because degree of numerator is less than degree of denominator, this is proper rational function. And to find out its Laplace transform, first we will write this function as a sum of partial fractions. So first we write 4s plus 5 divided by square of s minus 1 times s plus 2, and here I have this linear factor s minus 1 is repeated 2 times, and we know that whenever we have repeated linear factor we are writing two partial fractions corresponding to first power of s minus 1 and second power of s minus 1. Here we will write constants a and b, and corresponding to s plus 2 we write capital C in the numerator. And after writing in this way we try to find out values of these constants a, b, c. For that we multiply this whole equation by s minus 1 square into s plus 2. So on the left hand side we will have 4s plus 5. Here s minus 1 will cancel out and we will be left with s minus 1 into s plus 2 plus b times, here we have s minus 1 square, and if we multiply by this s minus 1 square into s plus 2, square of s minus 1 will cancel out and we are left with b times s plus 2. And here we have s plus 2, so that will cancel out and we will be left with square of s minus 1, and we give this number 1. Now because I have linear factors s minus 1 and s plus 2, first I take s minus 1 equal to 0 and I obtain s equal to 1. So first I find out value of constant corresponding to s equal to 1. So for that we take s equal to 1 in this equation number 1. So if I put s equal to 1 here, I will have 4 into 1 plus 5. This term will be 0 because if we put s equal to 1 we will have this term equal to 0. Similarly this will be 0 when s equal to 1, and we will have non-zero contribution from second term b times 1 plus 2. So therefore this is 4 plus 5, that is 9, equal to 2 plus 1 into b, that is 3b. Therefore b equal to 9 by 3, that is 3. Now we take s equal to minus 2. Another linear factor is s plus 2. So for that we put s equal to minus 2 and we see which constant we obtain. Here first we take s equal to minus 2, so I have 4 into minus 2 plus 5, and terms containing s plus 2 will become 0. So these two will become 0 and we will have c times minus 2 minus 1 whole square. Therefore this is now 4 into minus 2 minus 8 plus 5, that is minus 3, c times square of minus 3, which is 9. Therefore c equal to minus 3 by 9, and we obtain c equal to minus 1 by 3. Now to obtain value of remaining constant, which is a, we will compare the coefficients of powers of s on both sides. We can see that on left hand side we have polynomial of degree 1. So here power of s is 0, power of s square is 0, power of s is 4, and constant term is 5. So we can write down right hand side in terms of quadratic polynomial in S. If we simplify all these things, if we simplify the right hand side, we can have right hand side as something into S square plus something into S plus some constant term. So either we can write right hand side in terms of powers of S, and then we can compare the coefficients of powers of S on both sides. And if you are comfortable, we can directly compare the coefficients of S on both sides. For example, suppose I want to compare the coefficients of S square. Comparing coefficients of S square on both sides. Comparing coefficients of S square in equation number 1. On left hand side there is no term containing S square, that is coefficient of S square is 0 on left hand side. On right hand side we will identify those terms which are multiplied with S square. So if we simplify, if we multiply S minus 1 into S plus 2, we can see we will have S square plus S into 2, that is 2S minus S. 2S minus S is plus S, and minus 1 into 2. So we have S square plus S minus 2 into capital A. So from the first term, coefficient of S square is A. So here we write capital A, which is coefficient of S square from first term. In second term there is no S square, that is coefficient of S square is 0. In last term, if we expand this, we will have C into S square minus 2S plus 1, that is coefficient of S square in last term is capital C. So we obtain that 0 equal to A plus C, therefore C A equal to minus C. We have obtained value of C, so we write A equal to minus C, and value of C is minus 1 by 3, therefore value of A is 1 by 3. If we wish, we can compare the coefficients of S also. Suppose I am comparing the coefficients of S, then also my answer must be same. So for that we find out coefficient of S on left hand side, that is 4. So here we write 4 equal to, in first term coefficient of S is A, so here we write capital A. In the second term we have term containing S, and coefficient of S is B, so therefore we have to write A plus B. And in last term coefficient of S is minus 2 into C, so here we write minus 2 into C, therefore 4 equal to A, and we are having values of B and C. B is 3, C equal to minus 1 by 3, so I put B equal to 3, C is minus 1 by 3, and then I simplify A plus 3 minus minus plus 2 by 3, therefore value of A equal to, we take these two terms on this side, that is we subtract them from 4, so 4 minus 3 minus 2 by 3, 4 minus 3 is 1, so I have 1 minus 2 by 3, that is 1 by 3. So if we compare coefficients of S, then also we get the same answer, A equal to 1 by 3. So answer must be same, either we compare the coefficients of S square or S, or here we can compare the constant terms also. If we compare the constant terms, then also answer must be same. So we can compare either coefficients of S square or S or constant term to obtain the value of this constant A. And once we find out these constants, then we put their values on left hand side, right hand side. Left hand side is our function 4s plus 5 over s minus 1 square. So therefore 4s plus 5 divided by s minus 1 square times s plus 2. This now we have written as sum of partial fractions. Value of a is 1 by 3. So first factor was a divided by s minus 1. A is 1 by 3, so we write 1 by 3 into 1 over s minus 1. Second factor was b over s minus 1 square, and value of b is 3. So here we put b equal to 3, and value of c is minus 1 by 3. So b equal to 3, so here we write 3 into 1 over s minus 1 square. Value of c is minus 1 by 3, so we have minus 1 by 3 times 1 divided by s plus 2. So we have put values of a, b and c here. B equal to 3, c is minus 1 by 3, and a equal to 1 by 3. Now we take inverse Laplace transform on both sides. Therefore L inverse of 4s plus 5 divided by s minus 1 square times s plus 2. This is equal to 1 by 3 times L inverse of 1 divided by s minus 1 plus 3 times L inverse of 1 divided by square of s minus 1 and minus 1 by 3 L inverse of 1 divided by s plus 2. And we have ready-made formulas for all this. This is equal to 1 by 3. We are using this formula. L inverse of 1 divided by s minus a is e raised to at. So here a equal to 1. So this is e raised to t. Similarly, last will be, here we have L inverse of 1 divided by s plus 2. So if we compare s plus 2 and s minus a, value of a is minus 2. So L inverse of 1 over s plus 2 is e raised to minus 2t. And for this, we have to use the formula for L inverse of 1 divided by s minus a raised to n. So if you recall, this is e raised to at t raised to n minus 1 divided by n minus 1 factorial if n is a natural number. So here value of n is 2. So we take n equal to 2 and s minus 1 is there. So we will take a equal to 1. So this is going to be e raised to t raised to n minus 1, n equal to 2. So we have t raised to 1 divided by n minus 1 factorial, that is 1 factorial. So you must remember all these formulas. If you are not familiar with these formulas, then you cannot write inverse Laplace transform. So we are using this formula with a equal to 1 and n equal to 2. Now we can simplify this. This is 1 by 3 e raised to t. 1 factorial is 1, and this we write as 3 times t times e raised to t minus 1 by 3 e raised to minus 2t. And if we wish, we can take e raised to t common here, or we keep this as it is. So in this way we can use method of partial fractions to find out inverse Laplace transform of this type of proper rational functions. So all we have to do is we have to express our proper rational function in terms of partial fractions, and we have ready-made formulas for the inverse Laplace transform of this type of functions. So we are using those formulas. So I stop here. I hope you like this lecture. Thank you very much.